collecting some information from the end of the last lecture, so the first lecture of mine. So let me remind briefly that we are interested in Cartan geometries, and from my perspective, I'm not wanting to treat it in the way like having some structure, some equation or whatever, and then make some prolongations and end up with the solution to the equivalence problems, just building the Cartan connection and seeing the invariant, which helps us to understand the geometric structures in general. That was clearly the original aim. But from my perspective and for this lecture series, I would like to stress the approach where the Cartan connection should be viewed as something which is given, maybe constructed from some other data, but something like having, say, the Levi-Civita connection for Riemannian geometry, allowing you to use the connection and to have the calculus, like any other choice of a affine connection. The Levi-Civita one enjoys some special features, which allows you to see some things which you wouldn't see at the general level. But I'm interested in the calculus, and the calculus means we are going to try to see the natural operators, so the operators which are commuting with the things. And that's most simple at the level of the homogeneous spaces, because with the homogeneous, so with the Klein's picture, we simply deal with a homogeneous space G mod P, which we see as the model for our Cartan geometry. And the moral of all this development is that in some sense, nearly everything which makes sense and works for the homogeneous case, for the Klein geometry, has got some very good extension and analogy in the curved worlds. And that's the message I would like to say and distribute here. And so the difference between the homogeneous situation, where the first line over there, the structure equation, has got 0 on the right-hand side. And as well known, this is the equivalent condition to know that your space equipped with the Cartan connection is in the category of Cartan connections locally equivalent, so isomorphic to the homogeneous model. And omega in that case is simply the Maurer-Cartan form, which identifies the values of the tangent bundles with the values of the left invariant vector field. So identifying the Lie algebra with the space of left invariant vector fields. In general, because we mimic all the properties of the Maurer-Cartan form, which makes still sense, we can talk about the so-called constant vector fields, omega inverse of x for each element x in G, and the curvature on the right-hand side, the capital K. So I tried today to make the kappas much different from the capital K to please Rita. So if you plug into the big K, the curvature, the constant vector fields, you get a function from G to the space of cochains of the Lie algebra cohomology. So the two forms valued on the G mod P, valued in G. So it's the Lie algebra cohomology, is the coefficients in the adjoint representation itself. And clearly the curvature function is obtained plugging in the constant field. So the differential of omega applied to the constant fields doesn't have the first two terms, and what remains is only the evaluation of omega on the bracket, right? And then with the minus sign, and then there is the evaluation of the bracket of omega, but on the constant vector fields you just get the bracket in the Lie algebra. So that's absolutely obvious. And on top of all that, I made the assumption last time that we shall choose some complementary vector subspace identifying the quotient G mod P with the G minus, right? So in the real situations, in all the parabolic geometries, we have got the grading we saw in so many lectures here already, and the G minus is naturally the negative part, so the dual to the nilpotent radical in the parabolic subalgebra. So dual with respect to Cartan-Killing form. So and this is the standard fiber for the tangent bundles, right? Whereas the P plus part would be the standard fiber for the cotangent bundle. So if we fix the G minus, so we know that the curvature is a horizontal form, so it's enough to consider kappa only as valued on the G minus entries. And then again, just having in mind that the sections of the associate bundles, the homogeneous bundles, are just functions from the principal fiber bundle valued in the modules, P modules in general. If it's G mod P, we can use the constant vector fields to define a very nice operation which is called a fundamental derivative. It's the capital D, and the fundamental derivative viewed this way simply eats element from G minus and produces the derivative of the constant vector, well, in the direction of the constant vector field applied to the sections S, right? And then a nice thing is that we can also restrict this to values in the G minus, which we identify with G mod P, and we get what we called invariant derivative, which mimics very much the covariant derivatives, because the arguments there are the tangent vectors actually at the manifold. The drawback is that unlike the fundamental derivative, which is a natural operations, and you simply get the result applied so the fundamental derivative applied to a section S produces something which is in the tensor product of the module, where S is having values with the adjoint vectors dual, right? So this is no more true for the invariant derivative. It makes sense as something which produces functions again. So again, what we will have is that the nabla omega nothing S is a function on G valued in G minus star tensor V. That's okay, but it's no more P equivariant in general. So you can't say that it's a natural operator because it doesn't map sections into sections. Very recently we finally wrote down a paper with Andy Chubb which clarifies a geometric description in which sense this is a invariant operator, but I won't touch this at all. It will appear in the Vinogradov's memorial proceedings. So last time I thought I would be more effective and I would show you a proof of the Bianchi identity you see there and the Ricci identity, which is written down here already for the invariant derivatives. And I didn't manage, and I won't invest the time now as well, but whoever is interested, just come to see me in the tutorial tomorrow and I show how easy it is. It's really, from my perspective, it's sort of a meta proof of how beautiful and useful the Cartan approach is, because the Bianchi identity is a matter of a few lines of computation, and the result follows from the Jacobi identity on vector fields. And that's it, right? So it's straightforward, and Ricci is more or less obvious from the definition. And moreover, if you restrict to the situation I also try to show as the typical example everybody should know about, and that's if our G, so the group, is the affine group or a subgroup of it corresponding to some choice of G structure, then what we deal with is simply a linear connection on the manifold together with the soldering for understood as a Cartan connection, and everything splits because it's reducible, so it looks like it doesn't make much sense, but you see immediately then that the Bianchi identity with having this natural splitting of the G minus and G0 would simply give you immediately the two Bianchi identities which you know from elementary courses, but for connections distortion, which looks very complicated if it's done the classical way. So here it's just straightforward consequence. Right, let's go one step further and let's talk about the jets. So we want to see differential operators. So I will remind you that if we fix a P module V, then we have got a functor script V, which takes a manifold equipped with a Cartan connection of our type and takes the associated vector bundle. Of course, then an operator, say, well, I will call it D again, but it will not have the omega there, so no confusion with the fundamental derivative. D will be something which goes from kjets of V into, say, some W, and that's what we understand under linear, under differential operators. And if it's linear, because starting with a module, this will be a vector bundle, and it makes sense. So then this will be a linear map between the vector bundles, right? Everybody knows that, no problem. And the jet prolongation of the sections is, in some sense, a universal differential operator which gives you all the operators by composing the things here, right? Now, what can we do in our situation? In our situation, we can simply say that we take S and we map it to S, and here will be a morphism which takes X and maps it to omega minus 1x S. Right? So that's the fundamental derivative if we, so it's simply S d omega x, well, yes, so d omega S with free slot here, right? This is a well-defined thing, so you can view this as a module. So this is sitting in V plus G star tensor V, and obviously it's a natural thing, as I told and showed, and this corresponds to the action, and the action there is at the group level. It would be G acting on V phi, and it would be just the original action on the first slot combined with the mapping where we get the new homomorphism, right? So these are morphisms from G into V. And this will be going to, so we take a morphism B and we map it into, say, G dot phi, and here we have to act with the inverse acting on D. So that's the obvious action which is there, right? And now we should notice that if we instead write S, and again we just would write it, not this, but we restrict it to the G minus elements. So this would be in V plus G minus star tensor V, which looks very much like something we would like to see as jets. So this is then what I would call J1V. But what is the natural action there? You have to see that the one jets are sitting inside of this by requesting, so this is sitting inside of the V plus G star V by requesting that the homomorphism part behaves as we would like to see for a jet prolongation. And so we request that phi applied on Z must be minus Z acting on S. Right? Because we know that the fundamental derivative, if you plug in the vertical direction, and the Cartan connection reproduces the fundamental vector fields, and the section is an equivariant mapping from G to the module. So it must be the action by G inverse, but you want to see the level of the algebras. So inverse gives you the sign, and this is the action of the Lie algebra, right? For Z in P. So if I take a vertical argument, so the redundancy in the algebraic behavior of the fundamental derivative in the vertical directions gives you this canonical embedding of the one jets sitting in this bigger guy, right? And if you read then of the action, then it's as follows. Then it means that the action on V phi in the one jet prolongation of the module, the first jet prolongation of the module would be the following. So it would be just V phi. So we act with a Z. So this will be Z acting on V. So that's the first slot. Yes?
I'm sorry to be pedantic, but so G minus is inside the G. Now G star minus is not inside G star unless you identify them with some form, right?
Yes.
You're doing that?
Yes.
Okay. Happy. So you're fixing that form.
Yes, I was fixing the decomposition.
No, because you spoke about naturality. That's why
Yes.
I'm just being pedantic. Okay.
Yes. You can also, wherever I write G minus, you can write G mod P.
Sure.
And then it would be completely.
No,
I just write G minus as a
Okay.
simplification of the notation, right?
Fine.
So here what you get is Z acting on V. That's clear. Then you have, I will write, just to be able to write it, lambda will be just the representation on the module V, right? So that will be lambda Z composed with phi. Then there will be so that comes from where is it here? From this multiplication of G. It's the infinitesimal version. So instead of having it there at the same time, you have a sum, and you decompose this part for the horizontal and vertical part. So it will be phi composed with the small adjoint action, but that will be actually the induced action on the quotient, right? So I write at minus Z, and this is now acting on the G minus identified with G mod P. And the third one is the other half of this, and that's lambda of, and here it would be at the vertical part of the adjoint action of Z. I leave the argument free here, and this acts on V. So this is the expected way how the, well, not V but S. Yeah, also. Yeah, I wrote V here, so why not? So you expect these jets. You expect that the action must be splitting the values of the sections into the jets. Right, in general. It doesn't happen for the affine connections because there is nothing vertical except of G0 part which keeps going, so this will be simply not there, so there will be no action here. But in general you have to expect that, right? And that's the reason why the first jet prolongation is already a quite nasty quite nasty representation. Even if V was the most beautiful irreducible representation of P, the first jet prolongation is already quite nasty. So, what we get out of that is that we simply can write down the jet prolongation, so J1 of S, that will be the jet prolongation of the function of the section S, viewed as a function from the principal fiber bundle into the module, and this will be sitting for us in J1 VM, and what we mean by that is we identify the respective section here with S and the invariant derivative. So although the invariant derivative, so it means the restriction of the fundamental derivative to the G minus, is not natural and is not making sense easily, if you put it together with the S's here, then it does make sense, and it's a natural universal differential operator. So it shows you also that up to first order, of course, all the operators of first order will be given by some linear morphisms, equivariant ones on this, and therefore they will exist for all the curved worlds as well. So that's the simple part of what I claim, that there is more or less the same behavior, right? So here it's exactly the same behavior. So what about higher order jets? So if you take JKVM, so the question is whether we can write it as, yes, so here this one, just to be absolutely sure, so this one would be sitting in the sections of the associated bundle. Yeah, and technically you can view this. You take the homogeneous space, you take the space of sections, you take the first jet prolongation, and you look at the action of P on that. It preserves at the origin, right? So it preserves the origin, the P. Therefore, you have a well-defined action on the sections, on the jets of the sections. So this makes sense, right? Now the question is whether we can do the same for the higher orders. So would this be also, in some sense, equal to JKV? So this guy, of course, makes sense, because if you are the homogeneous model, then again, it doesn't matter whether you take first jets or case jets or infinite jets. You simply have the action on the group P, which keeps the origin, and so it induces the action on the germs of sections around the origin. So in particular on all jets. So there is absolutely no problem. But unfortunately, this is not true. This is not true. You can't identify in general these two things by having some natural differential operator, universal differential operator, which would go from here to here if k is bigger than 2. For second order it's still true, and we shall come to why in a moment or later. So for higher order it's not true. But what can we do? We can do a nice thing. We can say, so what? So it doesn't work for higher orders, but it does work for the first jets. So at least we can iterate the first jet. So what does happen if we iterate the first jet on such a formula? So it means you get the invariant derivative of S, and here you get the iterated invariant derivative. And the nice the nice answer is that actually that's what the people are doing, well, Eresman and others, and they would call it non-holonomic jets, right? So you simply take J1 of J1 of J1 k times, and that's a nice functor. But of course, no one would do that because it's too much redundant. But what you can do is to take the semi-holonomic jets. So the way out are the semi-holonomic jets. So the easiest way how to see it is on at the second order, right? So if you imagine the second order, so you have J1 of some bundle, say V. So you have, of course, two projections to J1 of V. One of the projections is the projection of the outer J1, just forgetting about the derivative part, and the other projection is the functorial value on the first projection here. So if you would write it down in coordinates, so it would be the second, so the first jets would have, say, coordinates xi and xij. And now if you take the next first order jet prolongation, then you would get, say, xij, so that's the derivatives of this x, and then you get some y ij or x ijk, which is the derivatives of this guy. And the outer J1 projection forgets this guy and this guy, whereas the functorial action forgets this guy and this guy. So if you want to find the equalizer of those two projections, we call it the semi-holonomic jet is the equalizer. So you simply want that these guys are equal, right? But here, you know that the second derivative would be symmetric. They are not, in general, right? And that's exactly what happens, because if we iterate J1 using this procedure, and we take the equalizer in the case order case, then we can see that if S is mapped to S, invariant derivative of S, the square of the invariant derivative of S, and so on, and we end with the case iteration of the derivative of S, then we get a universal operator which works, it's well defined, it makes sense, and it lives in the J bar K of V. So we have got universal differential operator which goes here. Again, if I go to the favorite example of the affine connections, so the group being the reductive case, so G is the affine group and P is just some GLN. Yeah. So then what we are doing, simply we take the covariant derivatives, we iterate the covariant derivatives, and so instead of landing in the symmetric jets, we land in the more general jets. But it's good to stress that actually due to Ricci and Bianchi, we do not land in every point there. Actually, the image of our jet, of our universal operator, is some quite weird and wild algebraic subvariety in the space which comes from this module, right? So this is again G cross P, and here I would write the semi-holonomic extension of the module, right? So actually with the universal operator, its values do not hit all elements here. So there is the restriction to an algebraic subvariety. Right, so that's the jets. So now for a moment let's come back to the homogeneous situation. Homogeneous case. So what are we doing there? So simply these iterated omega nablas are just the derivatives in the direction of the left invariant vector fields, and there is no curvature there at all, right? So what we get there, we can imagine that in order to see the jets, we simply, if we take the case iteration of nabla omega on S, then it acts in such a way that you take a word x1, xk of elements in the Lie algebra G, and you map this word into the action of the vector fields. So it means that actually you have something like an action of the elements of the tensor algebra of G, right? That's what it is, right? So whenever I take an element here, I can just say what it does with the section. Well, of course, on top of that, I know that if I take xy and subtract yx, so if I take the commutator, then I know that it must give the same as the commutator of them, right? So the action of the commutator is there. So actually what I get then is action of the universal enveloping algebra, because I have to quotient by the ideal which is generated by this equality, right? To have some injective thing. But still it's not good enough to get a dual to the jets, because the values are still in the module V, right? So this is, if I just hit the S, so it's still in V. Because I do it in the unit, right? Because I have the fixed unit in the G, so I can do everything there. So that's nice. So it means that I can sort it out taking the universal enveloping algebra and taking the dual of the module. But at the same time, there is still something weird going on, isn't it? Because I didn't say where the x's are coming from. I would like to see them as being only in the G minus, but it's not the right way, because I want to have them in G. But that means that I have to get rid of the redundancy of having the vertical pieces in the universal enveloping algebra acting algebraically. And this can be sorted out by, so if you take such a word, so let's say that all the x's are either from G minus or from P. So all those from P could be bubbled through here to the right end position on the cost of adding some commutators, right? Who cares? So in the end of the day, I just get to tensor over the universal enveloping algebra of P. And I get exactly the induced modules, right? And they will be in some sense dual to the J infinity of V, right? So if I take all the jets, but a dual. So that's a straightforward thing, and actually the people call it the topological dual because we always have only finite number of orders involved, right? So, and now we come to the beauty, right? Because that's the essential beauty we want to see, because unlike here, so forget about the curved situation in the semi-world here, right? So even if we were in the homogeneous case and we would just have the regular jets appearing here instead of the semi-holomic ones, still it's an absolutely horrible representation, and moreover it's only a representation of P. And what we got by this dualization procedure, we get a much simpler module, because this is something like polynomials, whereas the jets here are actually power series. So a much worse, much bigger object. And moreover, it's now a UG module. Right, so it's now a nice UG module because dualizing, you simply get rid of the problem that the horizontal derivatives increase the order of the jet. And therefore, if you get the truncated actions, it can't work because it's no more working. Whereas here, the horizontal derivatives are dualized, so they go down in the orders of the polynomials, and therefore it makes sense and there is absolutely no problem. So we see that actually linear equivariant, so I would write intertwiners, shorter.
I have a question.
Yes?
When you were speaking about the series and the polynomials, are perhaps assuming some nilpotency of these operators? No. This is only, a...
No.
interpretation. Okay.
No, that works. So I'm not yet in Verma modules, so this works on general level.
Yeah, that's why I was thinking.
Yes.
Yeah. Okay. No, fine.
I mean, it's because here you simply work with, we start with the tensor algebra. So each element there is only finite polynomial.
Yeah,
Gotcha.
because sooner if you do that, you get with the nilpotent operators when you push.
Yes.
Yeah, but that's not what you do.
No.
Okay.
No.
Thank you.
So the linear intertwiners are actually the same thing as homomorphisms of the modules, right? So you simply have linear intertwiners. So that was the D going from JK V into say W are the same thing as modules. So let me give it a name. So I will write say MV for this guy. Right, so homomorphisms over UG and P, and it goes the other way around, so it will be the MW MV. Right, so this is a obvious observation, right? You don't have to bother much. So that's
there should be stars, W star to MV star.
well, the stars are hidden here in the notation.
Okay.
Right. Yes. Now the next The next observation is what happens if we go to the curved case. And now I'm coming back to our old paper with Michael Eastwood, where we introduce the semi-holonomic Verma modules, but it works for general induced modules, of course. So what happens if we go to the curved case? So the first line remains as it is, right? Absolutely no problem. The second line does not. This one. What we need, I will make a, wherever they change, there will be a implication about this mark. So this holds only if one of the arguments is in the vertical direction, right? Because of the curvature. So simply the swapping the order of things here results in action of the bracket of the constant vector fields if and only if the curvature evaluated on them is 0, right? So in the homogeneous case, it's always the case. If we deal with general situation, we can't know. So to have something which is universal, we have to restrict the things here. And that's exactly what we call the semi-holonomic universal enveloping algebra with Mike. You simply have a much smaller ideal to quotient out. And of course you get automatically that the semi-holonomic UG projects to the holonomic one. You simply just quotient a bigger ideal which contains this one. So there is an obvious projection. So let's go further. Here we have got the same thing. We just have to make the bar here. UP remains as it is. So it's the vertical ones. We don't have to change anything. And what we get is the semi-holonomic Verma module. And what we get here is the dual to the semi-holonomic jets. Right? And now the claim will be different. So the claim will not be an equivalence between the space of linear differential operators intertwining the G action and the space of homomorphisms, but it goes only one way. It goes if you know a homomorphism, then composing with the universal jet prolongation will give you a invariant operator. And the invariant operator will work on the whole category of the curved Cartan connections of the given type, right? So only one way homomorphisms give us the intertwining operators. Right, so my time is going to the end today, so I will finish with technical step, which is then nicely used for the translation principles. So that's very good. And that's the Frobenius reciprocity. So the Frobenius reciprocity goes as follows. So we can imagine that we have got some homomorphism, let's call it D, like the operators, which goes from the UG with bar P homomorphism. Oh, that's something I didn't comment on. Actually, we don't need to know the G here. It works then for all choices of G. What we need is to know its Lie algebra and the subgroup P, the isotropy group. So at the level of the induced modules, the whole group G is not that much important now, right? of course, we know that if it's finite dimensional and nice, so the Lie algebra just gives us a few possibilities for the groups, right? But still, there are some topological freedom there. And if we have something like this M bar, say, as we have it there, M bar V, then what we can do is, so we can restrict it, right? Restrict to, say, D, which will be in Hom now only P, and it goes from W star to M bar V. So we simply know that in the semi-Holomy Verma module, like in the Verma modules, every there, you simply see the levels. So it's actually, there is a filtration starting with the module itself generated by 1. Then there is the things having just one entry of the algebra there, and then up to 2, and then up to 3, and so on. So you have a filtration like that, and you simply restrict to the very first level. So that will, and restricting to the first level, you have to restrict to P, because the other part would just throw it somewhere else, right? So that's easy, and vice versa. If we have such a D, so we choose such D, so we can write V x tensor F equals x tensor df for all x in the semi-holonomic U of G and F in W star. Makes sense, and it recovers the entire D, right? So the tensor products are over the right modules, as we want to see them. And finally, we see that just taking, say, D x tensor F minus 1 tensor xf, so defining on this guy, so it will be x tensor df minus 1 tensor dxf. But if we take any homomorphism, any p homomorphism, then we can exchange those things. So it will be x tensor df minus 1 tensor x df for all x in P. Right? So that's what we need, and that shows that taking any homomorphism D provides us with a nice capital D. So this shows the Frobenius reciprocity, which simply tells that these guys and these guys are the same. So it means we identify the Hom U bar G P M bar W M bar V Hom B W star M bar V. So understanding the P homomorphisms here, which is nothing but embeddings of the W star into the Verma module, the non-holonomic one, semi-holonomic one, is the same as knowing about the homomorphisms, right? And now of course, exactly as in the homogeneous situation, if our representations, so the P modules, are irreducible, then they are highest weight modules, and the semi-harmonic Verma modules will be again highest weight modules. So finding operators is not exactly the same as in the homogeneous case as finding the singular vectors. Well, so I will have to write it the other way around. Finding singular highest weight vectors in MV provides intertwining operators. Right, my time is over, I'm sorry, so you are a very nice chairman to me. So I will just conclude with one sentence. So this is the starting point for my third lecture tomorrow, because we shall use the fact that actually the singular highest weight vectors in the semi-holonomic modules, if projected, because this projection just induces the projection of the semi-holonomic ones to the holonomic ones, produces again highest weight vectors, singular highest weight vectors. And so our question for if we extend operators is rather the question about there is a covering of the singular highest weight vectors in the homogeneous situation by the singular vectors in the non-homogeneous ones. And in many situations, we are not yet ready in general, but in many situations, whatever can be obtained by translations, in the sense of Jansen-Zuckerman translation functors, in the homogeneous case, can be covered. And that was the result of the paper with Mike. I will try to show you tomorrow. Questions?
You speak about highest weight, which means a choice of positive system, but you have to choose wisely, don't you?
Yes. I mean, I'm now ahead of time. Tomorrow I will be talking about parabolic geometries exclusively.
Exactly. You need to choose wisely,
Yes.
not any positive would do.
Yes, sure.
Okay.
Any other questions? Right, let's begin again.